So, hello everyone. My name is Varad Dove, and I'm a doctoral student at the Department of Chemical Engineering at Kanpur. So, we'll start the session we'll give another couple of minutes for other people to join, and then we'll start sharply at around 7:05. So, within 5 minutes, we'll start the session. Okay. Okay. Hello. So, I hope you can hear me. I'm audible. Can anybody of you confirm? Hello. So, let's start. So, I welcome you all to this first lecture of advanced thermodynamics and molecular simulation. So in today's class, we are going to solve some sample problems which could help you in solving the week 0 and week 1 assignment. So initially, we'll start with the probability, as you may have also studied in the first week that we have introduction to the course only. So we'll start with the a brief introduction to you, a brief revision of your probability theory, permutation, combination, and all, which is highly going to be an essential part for this course. And then later on, we'll also do some revision to the our basic chemical engineering thermodynamics or normal thermodynamics. That's the first law, second law, and third law, right? So we'll start with the first question. Okay, the first question for today is. So I hope I am audible to everybody, right? Can anybody of you confirm? Yeah. Uh, Hello. Okay. Thanks. Thanks. We'll start with first question. Okay. My screen is also visible to everybody, right? Yeah.
Yes.
Thanks. We will start. Yeah. So for the first question which we have is so I'll first read out the question and then I'll write. A three-digit number is selected at random, right? And at random means that we assume that all the numbers have the same probability of being selected. So what is the probability that all the three digits are same, right? So what we have, so I'll write down the first question. So a three-digit number. Now, how is that three-digit number? That is a number from 100 to 999, right? Is selected at random. Now, what is at random? At random means that we assume that all the numbers, that is 1 to 0 to 9, all the numbers to have the same probability of being selected, right? So now what we want is, what is the probability that all the three digits are same, that all the three digits are same. So the options which we have are 8 by 100, option B is 9 by 100, option C is 7 by 100, and option D is 1 by 100. So what we have is, so let us first read the question. So what we have is, we have to choose a three-digit number, right? So let us draw a three-digit number. Let us assume that this is a three-digit number. This is the units place, tens place. So this is units place. Then this is the tens place. This is the hundreds place, right? So now what we have is, we have a three-digit number from 100 to 99, right? So we cannot put 0 in here, right? Now why? Because if we put in 0 here, we'll have a two-digit number. However, we can put 0 here or here. So that has to be kept in mind when you are going to solve the question, right? And it is selected at random. At random, that means that this number can anything from 0 1. So probability of having a 0, choosing 0 is equal to probability of choosing 1, which is equal to probability of choosing 2, and so on and so forth, right? So that is described here, that at random means that we have assumed that all the numbers to have the same probability, right? Then what we want is, what is the probability that all the three digits are same, right? So all the three digits are same, that means we can have 1 1 1 or 2 2 2, so on and so forth, right? So I'll give you a couple of minutes to try out the problem. But if anybody has not understood the problem, then they can unmute themselves and ask. Else those who have understood the problem can try to give me an answer. So I'll give you a couple of minutes to try it out. Okay. So I'll keep this question here. Is the problem understood is the problem very clear for everybody? If you do,
Yes.
okay, right. Okay. So if you have anybody has any doubt, they can ask. So anybody has any answer, so they can let us know. Let me know.
1 by 100.
Yeah. So one guy has the answer. What's your name?
Naishad.
Nation. Okay. So anybody else has the answer? Anybody else has the answer? So Nishat, can you tell? Can you explain it to us that how did you solve? How did you approach the answer?
There are 900 possible ways.
Nine.
Possible ways are 900, uh, 100
Okay.
to 999.
So
But
how did you
we
calculate
have
that? How do you know
that
that?
the possible ways of getting answers are 9, but total number of ways are 900.
Okay. So it will
So
be.
9 divided by 900, 1 by 100.
So how did you calculate that total number of ways are 900?
100 to 999
Acha, you
means
manually
total.
calculated. Okay.
So
Like for
100 to,
example, if example I give instead of 3-digit number, if I give 10, let's say for example, I give, let's say like this, 29998. Then how will you calculate? How will you approach the problem? Let's say instead of 100, I have the minimum number as this, maximum number is this, and I want a 5-digit number. So let
so
us do like this. So in
so
that case,
I in that
yeah,
case I use a multiplication,
yeah,
means or
yeah. So so in this case, let us make it easy. So let's do it 9999. Okay. So how will you calculate now?
now in that first the probability of getting
Okay.
one number is 1 by 9
Okay.
multiply by
1/9.
probability of
Okay.
probability of getting 1 at the second place is 1 by 9.
Okay.
In third place
It's
is
again 1
also
by 9. 1/9, 1/9, 1/9. Right?
hmm,
Is this what you is this how we will calculate? So this is what? This will be the numerator or denominator. Okay, okay. So let us first jump back to this question. So anybody else has the answer for this question apart from Nisesh? Yeah, so we have, so nobody is willing to tell. Yeah, so let me try to explain it. So the Nisesh give correct answer. It's 1/100. Okay, but I will let you know the approach, the correct approach. Right? Let us try to find a solution. So what we have a 3-digit number. So the way we will do it like this, right? And what we need is we need the probability, right? So the probability which we want, probability needed or needed, right? That is going to what? Total number of ways. Total number of ways to get a 3-digit number. 3-digit number with same digits divided by total number of ways of getting a 3-digit number, right? Right. So let us try to find. So let us denote this as the numerator, this as the denominator, right? So what we want is probability, and let us denote this as probability. right? So P is going to be n by d. So now let us try to calculate what is n. So n is going to be total number of ways to get a 3-digit number with same digits. So let us assume that we have an arbitrary 3-digit, right? So these are the 3 digits. So now let us assume that these are the boxes, and what we can put in are the like these numbers 4, 5, 6, 7, 8, and 9, right? So in how many ways can we fill this box? This box, yeah,
ten,
this one, right? So the
10,
total number of ways in which we can put this box is 10, right? So how many? So then in how many ways can we put this box? Can we fill this box? Can anybody answer?
10,
10 again, okay. And then how many ways? This one,
9.
9. So why are you saying that this is 9 and this is 10? Acha, because you are considering 0, right? Am I correct?
Yes.
Okay. So anybody else would like to answer? Yes, people are. Can you please explain? Okay. So I'll explain the question once again for those. So what we have to choose a number between 100 to 9,999. Okay. And that the digits are to be selected at random. And what we want is we want to have the what is the probability that all the 3 digits are same, like the number which we are considering, it could be 111 or 222, right? So this is the question. The correct way of doing this, this is not a correct way. So why is that? It's because now it is very clear that we cannot have 0 in this place, right? So clearly that number would be if 000 is not an option, right? So that is why 0 can, and all the digits are same. That is why 0 cannot be at this place. It cannot be at this place also, right? So it could not be this 10. If you are considering this as 9, then this is could not be 10. So it has to be one of the possible answer could have been 999. But that is again not correct. Now why? Because the digits are going to remain the same. Once you have chosen the digit for this, it is going to remain the same for all the things, right? So this, so let me make a new one. So this you can put it, this box you can fill it either with 1 or with 2 or 3 or 4 or 5 or 6 or 7 or 8 or 9. So the total number of ways in which you can fill this box is 1 2 3 4 5 1 2 3 4 5 6 7 8 9, right? So the total number of ways in which you can fill this box is 9. Now let's suppose that we have chosen a number as 4. Okay. So now you are filling now you have filled this box with 4, number 4. Okay. So let us draw here. Okay. So now you have filled this with 4. So now by compulsion, because all the digits are needed to be same, you need to fill this box. The total number of ways in which you can fill this box is 1 only. Whatever you have chosen here, so it has to be 4 here. Similarly, it has to be 4 here again. Right. So variability you get only in choosing this box. Right. So the numerator, what I am saying is it's going to be total number of ways in which you can fill this box is going to be 9. Total number of ways in which you can fill this box is going to be 1. And again, total number of ways of putting this is 1. Okay. So the numerator, that is, let us do this. Okay, so the total number of ways in which we can fill this box is 9. This is 1, and this is also again 1. Okay, that is why total number of ways to get a 3-digit number with same digit. This is going to be 9 into 1 into 1, and which is also very apparent from this question, right? So even if you don't know this, you clearly know that the total number of ways could be, this could be one of the number, this could be one of the number, or this, or this, or this, or this, or this, or 888, or 999. So total numbers are 1, 2, 3, 4, 5, 6, 7, 8, 9. Right? So you can always cross check. Okay, so total number of ways are going to be this one. Now the question arises, what is going to be the this part, right? So let us assume here we have a 3-digit again, the same number, right? So how many total number of ways of getting a 3-digit number, right? So you can fill it with what? You can fill it again. It could be 0, or it could be 1, or it could be 2, or it could be 9, right? Again, this, it could be 0, it could be 1, it could be 2, or up to 9. However, this you can choose. You cannot put 0 here. If you put 0, it's going to be a 2-digit number, right? So instead of that, what you have the option of filling this box with 1 or 2 or up to 9, right? So the total number of ways are going to be how many? This you can fill in 9 ways. This you can fill in 9 ways. Sorry, yeah. So sorry, this you can fill in 10 ways. This you can fill in 10 ways, and this you can fill in 9 ways, right? So let me go to the next page. Therefore, total number of ways of selecting a 3-digit number from 100 to 999 is going to be, remember, 10 into 10 into 9, right? 10 into 10 into 9 is going to be 10 into 10 into 9. Therefore, the probability which we want is, yes, so this is going to be nothing but d value, right? So this is d value, and this is going to be the n value, right? And what we are going to find out, we need this one, right? So that p is going to be just nothing but p is n by d. So n we have is what? N is going to be 9 into 1 into 1 divided by d value, which is this one, 10 into 10 into 9, which is what? 1 by 10 into 10, which is 1 by 100. Okay, that is the answer. P is going to be 1 by 100, right? This is the option, right? So anybody has any difficulty in understanding this? I hope this is very clear to everybody. Yeah. No, it's a thermodynamics class. Okay, right? So let me just tweak this problem. So instead of 100 to 99, if we had 1000 to 999, then what would have happened is, again, let us solve this one, that we are choosing a number between 1000 and 9099. So again, we would have chosen like this. So total number of ways of filling this is how many? 9 ways. This is going to be 1 ways. This is 1 ways. This is 1 ways. So in that case, numerator would have been 1 into 1 into 1 into 9. And for denominator, we have 10 ways of filling this one. 10 ways of filling this one. So 10 in how many? 0, 1, 2, like that up to 9. Okay, again this 10 ways of filling this one and 1 way of filling this one. So denominator would have been 1 into 1, sorry, 10 into 10 into 10 into 1, right? Therefore, the probability in that case would have been 1 into 1 into 1 into 9 divided by 10 into 10 into 10 into 9. So this would be 9, right? So in that case, probability would have been 1 by 1000, right? So I hope this is clear to everybody. If you have any question, you can ask. Okay, so we are going to I am going to upload this lecture. It's already being recorded. Okay, so you'll get a recording of that onto that NPTEL portal, right? So no need to record now. Okay, so if anybody has any doubt, they can ask. Otherwise, we'll move on to the next question, right? Is this clear to everyone? Okay, so I hope this is clear to everyone. Now we'll move on to the next question. Okay, so the next question what we have is again a permutation combination question. Okay, so this I told in a very simple manner. Similarly, if you are aware with the terminology of permutation and combination terminology, that is combinatorics terminology. So it's like NCR permutation. We denote permutation by NPR, and combinatorics terminology is NCR. So this means so this permutation means total number of ways of selecting R things out of N things, in which the way in which you choose matters, whereas combinatorics means total number of ways of selecting R things out of N things, in which the way you select does not matter, right? So let me use a different color. This is nothing but NPR, and this is NCR, right? So NCR is going to be its exponential is going to be n factorial by r factorial into n minus r factorial, right? Whereas a factorial is nothing but a into a minus 1 into a minus 2 up to 2 into 1. Okay, whereas NPR is going to be n factorial divided by n minus r factorial, right? So the way in which we can solve this 3-digit problem is you have a digit here. Using this terminology is you have a digit here. So this out of 9, you have to select one, right? Digit. So 0, 1, 2, sorry, not 9. Out of 10 digits, you have to select one, right? And then out of that one digit again, you have to select one. Again, out of that one digit, you have to select one. So in this case, the denominator, that is a sorry numerator, that is a total number of ways of selecting a number with the same digit would be 10C1 multiplied by 1C1 multiplied by 1C1, whereas denominator in that case would be out of 10 you have to select one here, then again out of 10 you have to select one in here, then out of 9 you have to select one in here. So in that case, probability is n by d, which is again 10C1 1C1 1C1 divided by 10C1 10C1 into 9C1, right? So this cancels out, which is, so let us go. So probability was 1c1 into 1c1 divided by 10c1 into 9c1, which is what? 1 factorial by 1 factorial, 1 minus 1 factorial multiplied by 1 factorial, 1 factorial divided by 1 factorial into 1 minus 1 factorial divided by 10 factorial, 1 factorial, 10 minus 1 factorial multiplied by 9 factorial, 1 factorial multiplied by 9 minus 1 factorial, which is what? So 1 factorial is what? Is 1 only. Similarly, 0 factorial is also 1, right? So this is 1 by 1 into 1 multiplied by 1 by 1 into 1 divided by 10 into 9 factorial divided by 9 factorial. So this 9 factorial cancels out, multiplied by 9 factorial into 9 into 8 factorial, right? Divided by 8 factorial. Sorry, it should be 10 factorial here, right? It's going to be completely different. 10 factorial, 9 factorial, 1 factorial, right? So this again comes out to be, if you look at again, it again comes out to be 1 by 100. So if you're familiar with this terminology, you can solve this way also. And the relationship between this NPR and NCR is what? This value, right? That is NP is NPR is going to be NCR multiplied by R factorial. Okay. Okay, so similar way, we'll solve one more question for this. Okay, for permutation combination. Okay, so the second question is, how many ways a cricket team of 11 members can be selected out of 15 members? The option which you have is 1465. Second option is 3794. Third option is 1365. And the fourth option is 656. Can anybody give answer to this question? So I am hope that I am audible to everyone. Yeah. So does anybody have any answer for this? So I'll wait a couple of minutes for you to solve.
11C15, no?
11C15. So what is that value? So why C? Why have you chosen 11C15? Why not 11 P50? Actually, that's the right answer. 11C15, 15C11, sorry. But yeah,
15 into
15C11.
14 into 13 into 12 divided by 11.
Yeah,
So 11 factorial goes, then we are left with 4 factorial. 15.
yeah. So 11C15, right? 15.
4 factorial will be 4 into 3 into 2. 4
Yeah.
3 are 12, 12 to 24. Above is 12, 12 divided by 2. So 15 into 13 divided by 2.
11
15 into
factorial
13 would be
multiplied by 4 factorial, which is going to be 11, 14, 13, 12, 11 factorial divided by 11 factorial into 4321, right? So now this 11 factorial goes away. 4 3s are 12, 12 also goes away, which is 7, which is going to be 15 into 7 into 30, which comes out to be this one.
1365. Yes.
Yeah. But my question is, why have you chosen this 11C15? Why not 15P11?
It is number of ways.
Yeah. So this is also number of ways. Why to go with this? Why not to go with this?
Same player cannot be repeated.
That is not that is very close answer, but not exact answer.
There cannot be interchangeability, na? That is why.
Yeah, yeah. Now that's very good. That is right answer. That you cannot have that the number it doesn't matter how you choose, as long as the actually basically the number of ways does not matter. It's just that if he or she is in the team, he's in the team. It does not matter whether we are selecting him for the first in the first trial or second trial or third trial, which is counted here. So we are, if we use 11p 15p11, we are counting those things again and again, right? So that is correct answer. So 11 C50. Now let's move on to the third question. Now this is a very good question, and I hope this would be the last for our this one permutation combination. Okay, so a club consists of a club consists of 50 members. Okay, so now the first question is, in how many ways can a president, vice president, secretary, and treasurer be chosen? So this is the first one. The another, in how many ways can a committee of 4 members be chosen? Okay. So the answers are options are two only. One option is 50 P4 and another is 50 C4, right? So which one is which? Anybody has any answer?
First one is A, second one is B.
So this one is 50 P4 and this one is 50 C4. Now why is that? Right? Why is that? This is correct answer. Because here the number the rearrangement does not matter, whereas here it matters. Then the way you take here matters, whereas here it does not matter. Yeah. So what is that? Yeah. So I hope this is clear to everyone. If it's clear, then we'll move on to the next question, which is based on our thermodynamics, concepts of thermodynamics. Okay. So the fourth question will go. So among which of the following are intensive, right? Which of the following Following are intensive properties. So I hope everybody knows what are intensive and extensive properties, right? Intensive properties. Following are intensive properties. So option you have is volume, temperature, C, number of particles, right? And the last option would be internal energy. What are intensive properties? Let me just give a brief for those who don't know. So in thermodynamics, we define certain things as properties, right? So properties are basically things for which we can write a complete derivative. Let's, for example, we have m, which is a property as a function of x and y. Okay. So for that, we can write dm, which is nothing but some. So m has a total derivative and it is a function of both x and y. So it's a two-dimensional property. So we can write m as a dx plus b dy, right? Where a is nothing but dou m by dou x at constant y dx plus dou m by dou y at constant x dx. Sorry, dy, right? And one more would be, this is the first property of first basic necessity for a thing to be called a property, and another would be dou a by dou y at constant x is going to be dou b by dou x at constant y, right? In other words, this also means that second derivative exists, right? The order in which you do that in which you take the derivative does not matter, right? So these are the properties. These properties again are classified into two properties, two ways. One is intensive property, another is extensive property, right? So intensive properties, let us move on to the next. So properties, we have two, intensive and extensive, right? And for property m, which is a function of mxy, so we should have dm equal to dou m dou x dx plus dou m dou y dy at constant x and at constant y, and dou m dou y dou x has to be equals to dou m dou x dou y. Okay. Now these intensive properties, these are the properties which are independent of mass. Okay. So let me write this down. Intensive properties, these are independent of mass. Properties, these properties are independent of mass. These properties are independent of mass of the system. Whereas, okay, so it is independent, okay. Whereas these properties are dependent on the mass of the system. Okay. Dependent, right? Right. So now, which of the following? So volume is an extensive property, right? Because it does depend on the mass. Let's say, for example, you have a balloon with some quantity of air. Now, if you change that, let's say the volume is V1. Now, if you change that volume from V1 to V2, the amount of material can change, right? So this is an extensive property. Temperature, it does not depend on the amount of substance, right? So if you have a substance, let's say a block A with temperature TA, Now, if you split this one into two parts, let's say A dash and A double dash, the temperature A dash and A double dash is going to remain same, and it's going to be equal to the original temperature, right? So this is independent of mass. That's why it's an intensive, right? Number of particles, by definition, it is dependent on the mass. So this is an extensive property. Similarly, internal energy, this is also similar to, like, for example, potential energy or Gibbs free energy, or any some sort of like that energy. So it's also going to be an extensive property, because it's going to depend on what is the quantity of matter which you are considering, right? 1 kg of water is going to have different internal energy than 2 kg of water, right? It can have. That's why the which of the following, so correct answer would be option B, temperature. So only among this, temperature is the intensive property, right? I hope this is clear to everybody. If anybody has any doubt, they can ask. Else, we can move on to the next one. Yes, Bishwajyoti, you have question. You can unmute and ask. Hello.
No, sir, that was
Okay.
audio
So
only.
earlier question, you had any doubt? Is the doubt clear, or you can ask again? I can discuss again. You have doubt for any other question? Earlier questions?
It's clear, sir, clear.
It's clear, na? Okay.
Yes, sir.
Anybody else has any doubt? If not, I see. I think. Okay. Thanks. So we'll move on to the next question, which also I hope that I know that these questions are very basic, but still we'll just do it very quickly so that it's clear for everybody else, right? So this one is question number 5, right? So we have let me call let me give you here. So this is the name of the process. Name of the process, and you have to tell me which property is constant. Which property is constant? Okay. The first one is isothermal process. So in isothermal process,
Temperature is constant.
what is constant?
Temperature.
Temperature, yeah. That is correct. The second one would be isobaric process. So here what is constant? Pressure is constant. Very good. Pressure is constant. Third one is let us call this isochoric process. So what is constant here?
Volume.
Volume, yeah. Good, very good. Volume is constant. Fourth one would be isenthalpic process. So what is constant here is? So what is here? Enthalpic process. Isenthalpic process, right? So iso means same, and the word that follows, that means that is the property, right? So thermal, it's very clear, it's the temperature. Baric means pressure. Choric means volume. So isenthalpic means what is going to remain same?
Enthalpy.
Enthalpy, yeah. Which is nothing but H. So if we are going to denote V, volume is V. Then the last one is adiabatic process. Adiabatic process. Does anybody know what is this called?
Q is constant, sir.
No
Q
heat
is constant. Q
Q.
is constant. Okay.
No heat transfer.
No heat transfer.
Yeah.
Anybody else?
But if it is a reversible adiabatic, entropy will be constant.
Yeah. So let me call reversible adiabatic means entropy is going to remain constant. Okay, anybody else? Actually, everything is correct. So adiabatic process means there is no heat transfer between the system, right? And if the process is reversible, then we have an entropy, constant entropy process, right? That's called as isentropic process, right? So let's move. Now the next question is about the equilibriums, right? So let's say we have a system A, and let's say we have a system B. Now, if these two system, if I am saying that these two systems are in thermal equilibrium, that means which property is constant? Let's say the temperature is Ta, the temperature is Tb. So in thermal equilibrium, we have equality of temperatures, right?
Temperature
Temperature.
constant.
Yeah, very good. Now this is going to be first one. Let's assume that we have a second, in which, let's say again the same system, system A, system B, and let me tell that the here the energy is constant. Let's say energy of A, or thermal equilibrium, sorry, pressure. So we have pressure of this system as A, pressure of this system as B. Now if PA is equal to PB, then we call it as which type of equilibrium? Anybody has any answer? So first of all, is everybody very clear about the concept of or the difference between equilibrium and steady state? Is everybody very clear about this? What is equilibrium? What is steady state? If I ask what is the difference between an equilibrium process and steady state process, can anybody tell me?
Steady state means it is along with the time, it is constant.
Okay,
Whereas coming to equilibrium, that is equilibrium of temperature means any point it is equal.
any point. Let me take an example. Let us take that this is a bar. This is, let's say, iron bar. Okay. Let's draw it properly. Okay, let's call this as iron bar. And we have an environment, let's say air. Okay. So now let me say that there is a candle and I'm heating this one. Right? So now what is going to happen? Let's say this is a temperature T0 or T infinity. And let's say the total length is L. So now with this, let's say for example, this is temperature T1, at some temperature T2, this is T3, this is T4, right? So so can anybody explain what will be the value of T1, T2, T3, T4 at equilibrium as opposed to what will be its value at equilibrium, steady state and equilibrium? Can anybody tell how the temperature variation is going to be along the length when we have an equilibrium as opposed to when we have at steady state?
Equilibrium means the temperatures all are constant.
Okay. And
So
steady state
T1
means?
is equal, T2 is equal, T3 is equal, T4.
Okay,
And
very good.
Along with the time, the variation is same for the
Steady
T1,
state.
T2, yes, steady state.
Yeah. So in general, what you can have, let us assume that this is a problem in which let's say this is a T is equal to 0. There is no iron bar. Okay. And now suddenly at time T equal to some 0, you put the candle, right? Right? So how will you approach? So the temperature along x, let us assume that temperature, this direction is x. So this temperature along x is going to be a function of what? It's going to be function of its length, right? It's going to be
Yeah,
function of also at time,
correct.
right? Right. So
Yeah,
when we have tx as a function of only x and tx is independent of t, then what we say is, then this is what? Then this is steady state,
steady state, correct.
right? So there is no variation of temperature with respect to t, right? So this you can achieve, let's say at t is equal to 0, you can achieve this at t equal to, let's say, infinity, or t is equal to t1, right?
Yes, yes.
But still, even in this case, here temperature can be T1, here temperature can be T2, here temperature can be T3 or anything, right? But at steady state, all these individual temperatures are also going to remain same, right? So Tx is going to remain, it's not going to be a function of x or t. When this is the case, then we say that it is an equilibrium, right?
Yes.
This is an equilibrium. Whereas if it is a function of if it is not a function of t, then it's steady state. Okay.
Yes.
Anybody has any doubt? Yeah. Okay.
So here in steady state, that T1, T2, T3, T4, it may remaining along with the time, it don't vary. That is only. For example, here 10 degrees, 20 degrees, 30 degrees, 40 degrees we have.
Yeah.
After 50 minutes also, for example, if raises the temperature,
Yeah.
that for 20, 30, 40, 50. That means
Yeah.
is this the right, correct, what I said?
Yeah. So what we have is at steady state, the temperature, local temperature can be very different. This could be 20, this could be 30, this could be 40, this could be 100,
This could
anything.
be 50, correct.
Yeah. But
But
when it reaches in equilibrium, all these temperatures
all
are
are
going to
equal.
remain same.
Equal.
Right. So
Okay.
so it's like this. You can, if you want to plot this Tx, so it may be at t is equal to 0, something, temperature is varying, and then it will become a constant. Same.
Constant.
Yeah, sorry, it will become like this. Sorry, let me draw it again. So this is temperature, this is length, right?
Okay.
So
Yeah.
again, t is equal to 0, it will be something.
And it is equal to
Then
10.
let's say t is equal to t1, it's like this. But then when it becomes equilibrium, it's going to remain like this. It will become like this. Temperature is going to be same.
10.
Okay. Yeah. So now what we were talking about is equilibrium. So now when the pressures are going to remain same, then we call it as what? We call it as mechanical equilibrium. Okay. Other properties may vary, but pressure is going to remain the same. Okay. Then we call it as a mechanical equilibrium. And then the third type of equilibrium is chemical equilibrium. Here A and B, and here if mu A is equals to mu B. Now I hope this is this everybody knows what is mu A. This is chemical potential, right?
Yes.
Chemical potential. So if chemical potential of system A is equal to chemical potential of system B, then we say it is a chemical equilibrium. Now what is chemical potential? It's nothing but partial molar Gibbs free energy, right? dN by dJ at constant I, right? This is total. So it's like Gibbs free energy per unit mole or per unit mass or per unit kg of substance, right? So when, let's say for example, this has 10 kg of substance, this has 20 kg of substance, but here the Gibbs free energy is 100, let's say per kilojoule something, and here Gibbs free energy is 200 kilojoule, but 100 by 10 is equal to 200 by 20, right? Which is nothing but 10. So then we have something which is called as chemical equilibrium. Yeah. And when for the
Gases.
when all of these are in equilibrium, that means temperature is also same, pressure is also same, chemical potential is also same. Then we say that that special kind of equilibrium is thermodynamic equilibrium. Okay, thermodynamic equilibrium. Thermodynamic equilibrium. That means what? That means first one was what? The thermal equilibrium. That means if we have a system with thermal equilibrium plus mechanical equilibrium plus chemical equilibrium, then we have something which is called as thermodynamic equilibrium, right? Right, this is very clear to everybody.
Okay, sir.
Okay, so now let's move on to the next question, which is what is the value of, let us go, which question is this? Question number 7, right? Question number 7. Now what is it? When does, this is very easy question, when does a real gas behaves like an ideal gas? Anybody has any answer for this, or does it, you require option, or you can tell?
At low
Yeah.
volume.
At low
Volume.
volume. Okay.
At very high temperature
At-
and low pressure.
Yeah, low pressure and
And
Very high temperature.
high temperature. Anybody else has any option? The correct answer is this one. This is not. Now why? Why I will tell you. So now what is ideal gas? So let's consider that there is a container and there are molecules of ideal gas. Right? Let's assume that these are the molecules of ideal gas. Now, what is the basic assumption of ideal gas? Can anybody tell me? This comes from kinetic theory of gases, right? Kinetic.
Particles are having mass, but volume is 0.
Okay. Volume occupied, volume of gas particles. It's not particles, is negligible as compared to container volume, right? And what is the second one? Second assumption of kinetic theory of gases?
Potential energy is 0. No repulsion or attraction forces.
Yeah, no repulsion. So interaction. So in other words, what we, so no repulsive or attractive forces exist between molecules, right? That means in other words, what I can say, no interaction between the particles, right? So when I say there are, so now why these two conditions? But for real gases, we know that real gases are going to have volume and there are going to be some sort of attractive or repulsive forces between them, right? So now why do these conditions are met at high pressure, high temperature and low pressure? Can anybody tell me this? Physical, what is the physical significance? Why can we say? Does anybody know?
At a very low pressure, the number of particles will be very less.
Okay.
So they are volume can be
Yeah.
neglected with
Yeah,
total
very
volume.
good. Yes, yes. And for temperature, it's going to be when you know that there is a random motion between the molecules, right? And this random motion of molecule, if you remember that this is going to be that energy kBT, right? So that energy is directly proportional to T. Actually, it is root T, right? So now as the temperature increases, the energy of the system increases, and hence the randomness of the system increases, right? Because there is high velocity and high randomness, there are no the attractive or repulsive forces. They become very random. There is no one expression or one equation with which you can put this. That's why at high temperature, each particle acts independent of another particle. That is what we assume because of the high randomness. And that's why we say that at high temperature, the randomness dominates over the attractive or repulsive forces. And hence we say that there are very less attractive and repulsive forces. And that's why gas behaves ideally at high temperature. Okay. Because of this randomness, the higher the temperature, the higher the randomness. The higher the randomness, the lesser are the forces. The lesser is the magnitude of the forces. Okay.
Can it be comprehended like this? At high temperature, the kinetic energy dominates over the potential energy between the particles.
Yeah, you can also put in that way, right? Because the total energy is what? Total energy is kinetic energy plus potential energy. So now, if this is directly proportional, let's say for example to the rate T, and this has some weak independence, let's say linear independence. So now, as the temperature is going to increase, this is going to be dominant over this, right? So you are absolutely correct. Okay. Now again, I hope this is clear to everybody. Let me see the chat if anybody has any doubt. So we'll move on to the next question. Again, this question is also very easy, but I wonder whether you know its origin. What is this Cp minus Cv value for ideal gas? What is this?
R.
Cp minus Cv is R. Now, what is this Cp? But first of all, tell me what is Cp? Anybody can tell?
Specific heat at constant pressure.
Okay. Specific heat.
At constant pressure.
Heat at constant
Constant
pressure.
pressure.
Yeah. And what
At
is what is Cv?
at constant
Specific.
was.
Yeah. Specific heat at constant volume. And Cp minus Cv is R. And what is the value of R? 8.314, right? In SI units. Now, what does this mean? Cp minus Cv is equals to 8.314. What does this mean? Let's say some SI units. That means what is the relation? That means Cp is greater than Cv, right?
Yes, sir.
Right. Now, can anybody tell me why? Why this? So physically, let us start. Let me tell you. Let us assume that we have a container, right? Same container. Let's say this is filled with water. Okay. And now we are heating this container. Let's say. Now to heat the same container with same amount of, let's say for example 1 kg and 1 kg of water, let's say water. Now I'm heating the same water, but here I'm taking constant pressure. Here I'm taking constant volume. Now I need more amount of energy to heat the water. Let's say the water is at 298 Kelvin and I'm supplying some energy and it becomes 300 Kelvin. Okay. Now here also 298 Kelvin and 300 Kelvin. Now here I put in 10 kilojoules of energy. Here I have to put only 8 kilojoule of energy. Means I am using the same water, but I'm increasing its temperature to the same degree. But here I need more energy when I maintain constant pressure. Whereas here, I have to maintain less, I have to give less energy, right? Because energy given here will be what? Cp dt. dt is going to remain same. Cp is greater than Cv. Here it's going to be, let's say, constant pressure, constant volume, Cv dt. So now dqp is going to be greater than dqv because Cp is greater than Cv, right? So now why is this? Can anybody give me physical significance of this? This means, right, this is very clear to everybody, right? That means if Cp is greater than Cv, dqp is going to be greater than dqv, right? Does everybody agree with this statement?
Yeah.
Yes,
I
right?
think
Yeah.
U plus PV actually.
U plus,
Work
yeah,
done we have to take up.
yeah, very good, very good. So here what we have a surrounding also here, right? So now this surrounding is also, so we are going to, whatever amount of energy which we are putting in, a part of energy is going to go in heating this system. However, another part of it is going to have to work against this, whatever the surrounding is going to put in the energy, right? So we have to do work against the surrounding. So part of energy has to be provided in here. Whereas for constant volume, there is no such thing, right? Because constant volume we know work done is zero, right? Whereas here work done is not equal to zero. That is why this energy is more. Okay. Now, now this is very clear. But can anybody of you derive this expression? Why Cp minus Cv is equal to R? Do you know how, from where this expression comes? Does anybody know? Let's say, for example, here I said ideal gas, right? So we know this relation. But instead of this, if I say what is Cp minus Cv for van der Waals gas, what is this? Can anybody derive? Anybody knows how to do it? If not, then I'll do it.
P plus A by V square into V minus P equal to RT.
Sorry, Cp minus Cv is equals to.
Now we have to
What you said?
derive one by one, I think.
So how do you derive? Just in general, can you tell?
PV equal to nRT, then I will assume V constant. I will make
Okay.
change P. Then I will
Uh,
assume P constant. I will make V variable, something like this.
No, actually, you are partially correct. It comes from what are known as TDS equations. TDS equations with Maxwell's law. These are called as TDS equation. You are partially correct. I think I am not full. I don't remember the fully, but Cp minus Cv in general it comes to be beta square Vt by K something, where beta is coefficient of volume expansion, whereas K is isothermal compressibility something. Does anybody remember have heard of this expression or not? Or do you want me to derive this one? Because this is one of the very important, because in exams, like for example, GATE exams and all, they will not, everybody knows what is the Cp minus Cv. They might not even ask what is van der Waals. They might give their own equation of state, and then they might ask you to calculate what is Cp minus Cv value. Right? Does anybody want me to derive this one?
So please do it, sir.
Yeah, so right now I don't have it. But in the next class, I will do it this one, right? What is Cv minus Cv? This TDS equation, I'll go into detail. So initial 30 minutes I'll spend for this. Okay. So we'll go for the next one. Okay. So let us move on to the next question. Okay. Now this is a very, this might be a tricky question. Yeah. So let me write this down. Question number 9, let's see. What we have two particular systems. So let me first write the problem statement. So two particular system have the following equation of state, right? Following equation of state. And what is that equation of state? Let's say the system 1 has equation of state as T1 is equals to 3 by 2. Let me write this like this. 1 by T1 is equals to 3 by 2 R N1 by V1. Okay. And another system has a equation of state as T2 is equal 1 by T2 is equals to 5 by 2 R into N2 by V2. Okay. Where R is the universal constant, universal gas constant, universal gas constant. Okay. The mole numbers, that means the number of moles of the two systems are given by like N1 is equal to 2 and N2 is equals to 3. Okay. Now, given that the systems are separated from each other by a diathermal wall. So this is very important. A diathermal wall. Okay. And the total energy of the composite system. Composite means both system A and system B taken together. System is 2 into 3, 10 to the power 3 joules. Then what is internal energy of system 1 and what is internal energy of system 2? So let me first try to explain this one. So what we have is, let's for example, I have this system A, right? A container with some gas in it, and I have system B. Okay. Now, when I take these two systems, so this system is going to have some temperature, some pressure, some volume, some internal energy, right? This system is also going to have individually temperature. Okay. So TA represents temperature of system A, TB represents temperature of system B, P represents pressure, V represents volume, and let me not, instead of U, let me call this as EA. Okay. VB and EB. Right. Now, when I take these two systems together, now in that case, the energy I'm calling is as total energy, right? Which is going to be, because because energy is a extensive property, I can write ET as EA plus EB, right? Because energy is extensible, extensive property. I cannot write PT as PA plus PP, right? This is wrong. Why? Because pressure is not pressure is an intensive property. I can write volume, total volume is VA plus VB, because this is extensive, right? Okay, I cannot write TA is equals to T total is equals to TA plus TB. This is wrong, right? Because it's an intensive property, right? So now what it has given is, it has given me equation of state for this system, which is what? 1 by TA is equals to 3 by 2R into Na by Va, right? This is equation of state for this system. Now equation of state for this system is 1 by TB is equals to 5 by 2R NB by VB. Now what we have is, now we are going to connect this to system with a dithermal bond, right? This is a dithermal bond. Then what is, as soon as we connect this to system with dithermal bond, the properties are going to change. Let's say TA dash, PA dash, VA dash, EA dash. For this is going to be TB dash, PB dash, VB dash, and EB dash, right? But what it is saying that it has given these parameters that N1 is 2, N2 is 3, and this, but that one total energy of the system is going to remain same, right? That means total energy initial what, how much, EA plus EB, it is going to remain same even after that one, which is nothing but this one, 2.3 into 10 raised to power 3 joule. Na dash is going to be what, 2, and NB dash is 3, right? This is 3.
Sir, here diathermal means it is a thermally isolating. Diathermal means.
Yeah, dithermal means exactly opposite. Dithermal means it allows flow of energy.
Flow of energy it allow.
Yeah, it allows. That means
Only
energy can
energy
transfer.
only transfer
Yeah,
and material
yeah.
not transfer.
Material not transfer, right?
Okay.
So in that case, you can say this Na dash is nothing but Na only. Yeah. So it allows energy, flow of energy, but whatever amount, let's say this energy of initial energy was EB and initial energy is EA. Let's say delta E amount of energy has been reduced from this system. It travels from, so similar amount, exactly same amount of energy gets transferred here, right? So that in a way that total energy is going to remain the same, right? Which
Yes,
is going to be, so now what we are asked to find is, we are asked to find what is this EA dash, what is this EB dash, right? So so I will give you 5 minutes to solve this question. Can anybody come up with an answer? So I'll give you option also. So let me write it here. So option A is 1787.7 joules. So this is for UA, right? So I'm giving option for what is UA or EA, whatever. So these options are for that. Option B is 714.3 joules. Option C is 782.5 joules, and option D is 741.3 joules. So I hope the question is clear to everybody, right? You can try to solve the question. I'll give you a couple of minutes. Let me just see if anybody has any doubt. Yeah. I will share the recording. So it will be up. It will be uploaded on the NPTEL. That in week 1 there will be a new tab wherein you can have the recording of this lecture. Okay. So maybe in 2-3 days you will have the recording. So let me know if anybody of you has gotten the answer. Okay. I'll wait for you. Anybody got the answer? So anybody is solving? They need more time, or should I give the answer? I'll wait for a couple of more minutes. Anybody got any answer? Or anybody knows how to approach the problem? Anybody would like to share how they approach the problem? No? So remember, so the first thing which you have to remember, that because this is a diathermal wall, right? It allows the flow of energy. So let me give because it allows the flow of energy. This is in. In this case, what is going to remain the same is temperature of
Volume.
the system. Sorry?
Volume also remain constant.
No, not volume. Temperature is going to remain constant. Why? Because why? Because there is something called as, maybe you are not aware of it, something called as conjugate variables. Variables. Right? Like if you write the first law, what you have is du is equals to TdS minus PdV plus, for open system, if you write mu I dni, right? Where I is equals to 1 to n, right? So now this temperature and entropy, these two are conjugate variables. Pressure and volume, these two are conjugate variables. Chemical potential and number of particles, these two are conjugate variables. So now if entropy, so you cannot keep both the both two things constant. If temperature is constant, entropy will change. If entropy is changing, temperature will change, right? Similarly, there is a temperature and energy relationship between it. So for example, right, sorry, so what we have in here is, because this is a diathermal system, diathermal wall, this allows the flow of energy, and that is why the temperature is going to remain the same. Maybe I should have prepared question very clearly, in which I would have given this thing. So now you try to approach the problem again. Given that this TA is equals to TB, then in that case, how would you calculate this U1 and U2? Remember,
Okay.
these two are the equation of states, right? These two are the equation of state,
Hmm.
right? And again, we have TA is equals to TB, right? We know the value of N1 also and N2 also, right? So now can you try to find it?
We get a volume from this.
Yeah. So you will get what? Ratio of volumes.
Volume
Yeah.
ratio initially, and finally also after
Yeah.
thermal also we get the volume ratios.
Yeah, exactly. And
So
also you have this U1 plus U2 is also, this is going to be 2.5 into 10 raised to power 3,
correct.
right? Yeah.
Yes.
So based on that, you can find out. So I want you guys to again approach this problem, right? So you can take this problem as an homework, and in the next week when you come back, then we can discuss this problem in detail. Okay?
Sir, here P also constant.
Yeah, T is going to remain the constant.
P is constant. Okay. P. What
So
about pre?
Yeah, so
Uh,
basically I should have mentioned in the question. So question should be like temperature is going to remain the constant. Okay.
okay.
So that I
Sir,
did not mention. So temperature is going to remain the constant.
okay, sir. Sir, U is equal to PV. Whether we consider here U is equal to PV?
U is equals to, so U is equals to PV. It's not U is not equal to PV, right?
H is
H
equal to
is
U plus
equals to
PV.
U plus
U
PV,
plus
right?
PV.
Yeah.
But okay, H
Oh,
value.
again, and one more thing. Oh, this is my
Ah,
mistake. This is not
ah,
V. This is not V. This is not volume.
ah.
This is energy U.
Okay, right,
U1,
right, right.
U2, U1,
Then
U2.
okay. Now we get it, sir.
Yeah, this is
Okay,
U1 and
copied.
U2.
Okay,
Okay.
copied, sir. Now we
Uh,
get it.
you can try. Now this is straightforward. You can try it. Then we can
Okay,
discuss
we
again
get.
in the next week. Okay.
Okay.
So we'll start. We'll stop with the last question. Okay. Maybe last question. Last or second last. Okay. So this one is question number 9. Now let's go to question number 10. Last question. Okay. The value of delta H and delta S for the reaction. Let's say the reaction is C. Let's say the reaction is C, which is in graphite phase, plus CO2 is going to give us 2 times carbon monoxide. Let us not go how this happens. Let's just assume that this reaction happens, right? And the delta H for this reaction is 170 kilojoule, and delta S for this reaction is 170 kilojoule per mole. Okay, now what we are asked to find is at what temperature the above reaction becomes spontaneous. Yeah. So the main thing is reaction becomes spontaneous, right? So at what conditions this reaction becomes spontaneous? The options which we have temperature are 710 Kelvin. Option B is 940 Kelvin. Option C is 1111 Kelvin, or option D is 1000 Kelvin. Anybody has any know how to solve this question? So here will come Gibbs free energy, right? So Gibbs free energy we know is what? Delta G is equals to
H minus TDS.
delta H minus D delta S, right?
D delta.
And
Zero.
when delta G becomes 0, the process is
Delta H plus D
simultaneous.
delta.
Yeah, exactly. Very good. Process is spontaneous. right? So 0 is equals to delta H minus T delta S, right? So T delta S is going to be delta H. That means T is going to be delta H divided by delta S. But what is delta H? 170 kilojoule. 170 kilojoule divided by 170 kilojoule per mole. Sorry, this is joule. No, sorry, this is kilojoule. And
1000 we get.
entropy is in joules. Joule per mole. Joule per Kelvin, sorry. Joule per Kelvin. Okay. So now this will be basically in joules, this will be 170
1000
divided by 170, which is 1000 Kelvin. Right?
Yes.
Okay. So maybe we can just do one more, which is fairly easy. So when
Sir, at Gibbs free energy 0 only, why it is spontaneous?
yeah, so Gibbs free energy 0. So you will so now why, so this you must have learned in the your UG normal thermodynamics, but the molecular
is-
origin of this, why delta G is 0, why delta G equal to 0 is only spontaneous, why not delta G equal to, let's say, some random number? So this comes from something called as legendary transform. Yeah, legendary. So what is maximum? There is something called as maximization principle and minimization principle.
Okay.
Now that all you will cover in the upcoming weeks. I think it's in third week or second or third week.
Okay.
Okay, second week of this course, legendary transform.
Uh-huh.
That sir will teach. Okay.
Okay.
At that time also we can discuss. You can bring this to my notice if you don't understand what sir tells. Okay.
Okay.
So let's have one more quick question and then we can all go. When 1 mole of an ideal gas at 3 bar pressure and 300 Kelvin is expanded isothermally and reversibly with the external pressure held constant at 2.5 bar. What will be the work done? Okay, option is 454.7 joule, option B is 456.5 joule, option C is 411.2 joules, and option D is 459.8 joules. Okay. Remember that it's an ideal gas. Okay. And it's an isothermal process. Okay. What we have is, we know that work done is what? Delta W is
PdV.
minus PdV, right? That
Yes.
means if we do integral on both the side, what we have? W is equals to minus PdV. Now it's an ideal gas. PV is equals to nRT. Right? Let us assume that there are one. Okay, so this is okay. That means pressure is equals to nRT by V. Right? W is equals to minus integral nRT by V dV. Right? Number of moles are going to remain constant. R value is already constant. It's already said that it's isothermal. That means temperature is also constant. That means I can take this whole outside the integral dV by V. That means work done is what? Minus nRT ln V from initial volume to final volume, right? That means minus nRT into ln Vf by Vi, right? Or if I want to get rid of this negative sign, I can nRT ln Vi by Vf, right? So now let us look at, so this is our expression A. Now what we are given? We are given N is 1 mole, right? Here it is initially at 3 bar, so Pi is 3 bar. Initial temperature is 300 Kelvin, right? The process is isothermal, right? That means final temperature is also 300 Kelvin, and external pressure is held constant. Okay, that means Pf is 2.5 bar, right? Now, but there is no information about Vf and Vi, right? But we know that Pv is equals to nRT. That means, and this is constant. So P1 V1 is equals to P2 V2. That means V1 by V2 is what? V in so in this our terminology, it's going to be Pi Vi is equals to Pf Vf. This means Vi by Vf is Pf by Pi, and we know Pf is what? 2.5 bar divided by 3 bar. Just put all the values into this to get the final answer. Okay. So it comes out to be around. So if you take care of all the unit dimensions, it comes out to be around minus 454.750. That is option. Which option? Option A, not A. Yeah, option A. Right. Now, why there is no minus sign is because here you see work done. Right. Whenever we say work done, we just take the work done by the system is going to be negative. So we are asking without this negative sign. It's going to be the other option. Okay. So I hope this is clear to everybody. We have, I think, one question.
Yes, sir.
Yeah, yes. The recording of the videos will be available onto the portal maybe within 3 to 4 days before our next class. Okay.
So from where this question number 1 to 11 is being asked?
So this I prepared on my own.
So not in assignment, okay? Yeah.
These are not in assignment. So assignment, if you look at assignment, those are not this much numerically extensive questions. Those are, I think, mostly true and false based or statement based questions. So I think you will be able to solve those questions fairly easily.
So in final
Hmm.
exam, this type of question will come or assignment type?
Yeah, so final exam, actually I am not aware, but mostly usually we have 2 levels of questions. So some of the questions will be NAT type of question, that means numerical questions, which is what I am telling, and some of the questions are also conceptual based questions, which for example, like what is open system, what are closed systems. So they might give you four such system, like for example they might give you thermoflask, they might give you car engine, and they are asked to find which of the following is open system or which are closed system, like this. Okay. And you may also have, so as we go in the course forward, we will also be having some coding sort of things. So coding assignments you will have. So codes may also be asked in the exam.
Sir,
Right. Hello. Yes.
so can you show the questions real quick? I need to take screenshot from the beginning, please, sir.
Okay. Yeah. Actually, the recording will be available, but still, if you want, let me know when I should change the
Yes,
question.
sir. Next slide. Yeah.
Yeah. This will also be available. The slides.
Yes, sir. Next slide, please.
Next.
Yes, sir. Yes, sir. Can you scroll this slide?
Yeah. Maybe you can take now.
Yes, sir. Please, the next slide, please.
Yeah.
Please scroll a little bit.
Okay.
Yes, sir. The next page, please.
So this becomes a big one.
Yes, sir. I have taken, sir. The next.
This one.
Yes, sir. I have taken.
The last one.
Yes, sir. Last one I
Yeah.
just took. Sir.
Okay.
Thank you so much.
So this will be available maybe within 3 to 4 days on through the portal also. Okay. Yeah. So I thank you all for attending this class, and I hope that you have learned something, and we'll see each other again in the next class. Okay. So thank you for joining the class.
Thank you so much.
Yeah.
Thank
Thank
you.
you.
Thank you.